All right, so our next speaker is Shaoyun from University of South Carolina, and he's going to be speaking on analogues of Alladi's formula over global function fields.
Okay, thanks, Frank. Thanks for introduction. So today I would like to talk about analogues of Alladi's formula over global function field. So this is joint work with Lian Duan and Biao Wang. Okay, so first you might be wondering, so what is Alladi's formula? Okay. So this is a, So this is a formula actually give a relation between Mobius function and prime number theorem in arithmetic progression. So let's give some review some definition. So Mobius function is defined as usual. Yeah, only defined on square free number. So when n equals to 1, just equals to 1. Yeah. Then now you let the pi of x. So this is a complex number, a prime number less than x. So we know the prime number theorem tells us so pi of x has an asymptotic estimate x over log x. Okay? And it actually is equivalent to the series, so mu of n over n, okay, equals to 0. Yeah.
Excuse me, Shaoyun.
Oh, yeah.
We're still looking at your title slide. Did you intend to go on?
Oh, okay, yeah. Oh, you cannot see my slide? Oh, okay, I know what's going on. Okay. Sorry about that. Okay.
Okay, good.
Yeah. Okay, yeah. So it's good now? Yeah.
Okay. Yes, it's good.
Okay, yeah. Sorry about that. Yeah. Okay, so I just talk about the Mobius function. So this is the define as usual, and we take the pi of x, so this comes the number, a prime number less than x. So prime number theory, we know at such an estimate, asymptotic formula. And it's equivalent to the series, okay, so equals to 0. Yeah, this series equals to 0. And then we can do some very simple calculation. You plug n equals to 1. So you're gonna get the 1 by definition, and you move the remaining term to the other hand. So we can rewrite so this series like this way. So now in 1977, so Alladi proved the following result. Yeah, so you take the integer k and L comma k is the coprime. And you think of P of n, so this is the smallest prime factors of n. So now we have such a, so Alladi proved that such a result, yeah. So if you realize, so we color the number 1 and 1 over phi of k here. So actually you can think about this is density. Yeah. Okay. So the connection to the prime number theorem in arithmetic progression. So you look at this condition, and we have such an identity for all the prime which is congruent to L modulo k. So 2017, so Dawsey extends this result in terms of a Chebotarev density. Yeah. So that gives some definition again. So K, you think about the finite Galois extension, and we Galois group G, and you think about the prime ideal lying over an unnomified prime number. So we usually write the P over P, flex the P over P. And we define adding symbol, or this is just a Frobenius element. Yeah, Frobenius element. And you connect all these Frobenius element, you think about the unnomified prime, and you think about prime ideal lying over P. So it's easy to see. This is actually a conjugation classes in the Galois group. So Chebolev's density theorem tells us for any conjugate class, and you take the connection of all the prime numbers such that, so this conjugate class is also called the Frobenius class over P. So it's equals to C, we pick. So it's also have such an asymptotic estimate. So the order of C over order of G, again, you can look at this is a density. So 2017, so this is Dawsey's result. Yeah, Dawsey's result. And then from this theorem, we can actually cover Alladi's formula. Yeah. This is just a special K. You take a K, the cyclotomic field. So the zeta K, this is a case a primitive root of a unit, and the C is conjugate class of L. Moreover, actually 2 years later, so Sweden and Wu generalized the Dawsey formula. Think about the number field. Yeah, think about the number field. So that is to say, you think about the two number field, LK. So you have the finite extension. Yeah. So for this density, for the Chebotarev density, actually this is just one case of so-called like a natural density. Yeah. So Kural, McDonald, and Shanghai, so in 2017, and they give a result in terms of the natural density. So this is how we define. So the P is all prime, and you delta S, so this is equal to the limit of this guy. So if this limit exceeds, so we call this the natural density. And so this result, it turns out, can also recover Alladi's formula and the Dawsey result in a very, quite a very straightforward way. Yeah. So their work actually is work over any number field. Yeah. So the result we showed here is just a special case. Yeah. Just L equals to Q. So this is how we look at the recover Alladi's formula. So you take the S. So this is the prime number is congruent to L, and then the PNT in prime number theorem in arithmetic progressions give us the natural density just equal to 1 over phi of K. Oh, so by the way, phi is Euler torsion function. Yeah. So I might have forgot. Yeah. For any conjugate class C, so you take this set. So this is you have the Folobinian conjugate class just equal to C. So then Chebotarev density theorem tells us natural density just equal to order of C divided by order of G. Yeah. So moreover, you might wonder, is the Mobius function is the only function in such a has such a result? So actually, so one generalized the function, the Mobius function, to the other kind of arithmetic function. Yeah. So he did over generalization over Q. So this is the statement. So you take some arithmetic function and A over 1 equal to 1 and satisfy this condition. Okay. Now, if you take some subset, you have the natural density delta of S. Now, yeah, to prove such a result. And so the function, we have more choices. Okay, you think about the Dirichlet convolution mu of A. Yeah, mu of A. So here we just give one example. So it's also proved by one in 2019. So the Lovier function, so defined as usual, so also have such a formula. Okay, so in this case, so our A in the theorem, we can take equals to 1 for square number, otherwise just be 0. So it's just to recover, yeah, this example. Now our question is like, okay, what about the function field? Is the analogous result? Yeah, so the answer is yes. So before we pop out our theorem, so we give some notation. Yeah. So FQ is a finite field of Q element. And if we think about the function field, so the constant field is just F of Q. So we also need to define the prime, right? So it's called a prime divisor. Okay, so prime divisor in K, this is a discrete evaluation ring. So you have the maximum ideal P such that your constant field inside the prime divisor. And you take the connection, we use the same notation P. So for simplicity, we just write the P, the maximum ideal that belongs to P, okay? Because the maximum ideal is just a unique one whenever you pick a prime divisor. Yeah, so we also can define the norm. So the Q to the power degree P. So degree P is defined, so let's do, so let's do field and over FQ, this dimension. Yeah. Very natural way to define. Now we set all the divisor D. So actually, so this is just a binary form sum for most all P, for most all prime divisors. So your coefficient AP just equals to 0, almost about finite. Yeah. So the norm, so by definition, it's just the product of a norm, and you have the power coefficient AP. Yeah. So in our work, so we only consider the very special ones, or like a effective divisor, which is means all your coefficient just a non-negative integer. Yeah, for all prime divisor. If the coefficient is greater than 0, so we write the P divides D. P divides D. Okay. So we also can have the analogous definitions of a Mobius function in over function field. Okay. So when the divisor is just 0, so you just take 1. Otherwise, so you have some like you think about it, this is square free, like they are all distinct. So now you use a -1 to power K. Otherwise, that's 0. Okay. So we also defined the number of the prime divisor, which have the degree n. So we use a very similar denotation. And when X is the whole set of the prime divisor. So now we know the prime number theorem for function field give us this equality. Yeah, so your main term is the q to the power n divided by n. This table actually summarizes our main notation, which is compared with the notation in a rational field. Yeah, rational field. So in particular, so you can think in particular, yeah, so think about q to the power n just x. So n is be log x. So this is exactly that our usual prime number theorem in yeah, over q. Okay, so now to talk about our main result, we also give one more definition, okay, which is a new phenomena. This is a new phenomena, I mean, because it's not happened in over Q or in integer. Yeah. So d minus of d, so this take the minimal degree. So the p is a prime divisor factor of d. So we say d is a distinguishable. This is the mean there's a unique prime factor. So we say p minimum of d, which you have you get the degree d minus of d, the minimal degree. Yeah. Now we define a set, so distinguishes element. Okay, so this is the distinguishable by the previous definition, and your minimal prime divisor belongs to this subset. So any set you have the natural density. Natural density. Okay, so this is our main theorem. So give any global function field or just function field, and you have a natural density, and you can see, so that this is take the limit, or you check some the series, so it's over the degree, consider all the divided degree larger than 1, and we only think about the distinguishable. Okay, so you can, yeah. So this is a kind of analog like a definition from Q. Yeah, from Q. Okay, so we have such a result. So next slide. So let's give a schedule of proof. Okay, schedule of proof. So first, the key lemma. So we need. So it's called a duality lemma. Which lemma is give a relationship between the minimal prime divisor and the minimal degree and the maximal degree prime divisor. Yeah, there's a relationship between inside our lemma. Yeah, duality lemma. Yeah. So d plus, so it's the maximum degree, and the q of s. So this is the cardinality of all such a prime divisor. You get the maximum degree. Now by this duality lemma, so we can prove next intermediate theorem. So we translate our main result. It turns out. So the intermediate theorem is talking about. So left-hand side, this is some kind of what we want to show. And it could if and only if we can prove right-hand side. Yeah, okay, we prove right-hand side. So then our question is translated to you counting, or you take a value of the prime divided with the maximum degree. So here we have a lot of analytic number theory calculation. Yeah. Okay, so then our main theory is following. So you just take the function defined just equals to 1 for all n greater than equals to 1. And so we show this result. This is also called equidistribution of the prime divisor with the maximum degree. Yeah. Again, so this is basically the calculations coming from the analytic number theory way. Yeah. Okay. So now by this one, so yeah, so we get our proof for our main theorem. So next slide. So we are going to give some application. Yeah, application of our main theorem. So first, we can give an analogous result for the Dawsey result in terms of the Chebotarev density. You think about the Galois extension, so geometrical one, this is the mean. So L and K, you have the same constant field. Okay, you have the group G and the P comma LK. So this is just a Frobentin class of P. Frobentin class. So we only consider unnomified P. Yeah, and so this flag P is over P. So the set, so this Frobentin class set. So we have the conjugation C, and for the Chebotarev density theorem over function field by this equality in particular. So in particular, natural density just equal to order of C divided by order of G. So now, yeah, this is the result, yeah, for this case, yeah, for this case. So next, we also give application if we think about the finite field, okay? Think about the finite field. And actually, this is our original goal. So at the beginning, we think about whether we can give an analog of Alladi's formula over finite field. Yeah. And it turns out now it becomes to a special case of our main theorem. Yeah. So we think about the irreducible Monica polynomial. And we define the same quantity cardinality number, and you have the natural density, and you have the distinguished set. So where your smallest polynomial factor, you're inside the S, and so this is the result. Yeah. So again, so you think about the only distinguishable one, and you have the density, just a natural density. And then we also, so since we also know the prime polynomial theorem in arithmetic progression, yeah. So this is the analog result of Alladi formula in 1977 by the over finite field, yeah. So you take the two relative prime or the two polynomial, yeah, or irreducible polynomial. And you think about these sets of the connections of all irreducible polynomials, and then we know that, so the quantity, the cardinality of this set just equal to this guy, and the field of G, so this is the function field, Euler torsion function. Yeah. So in particular, so that we have the natural density, 1 over field of G. Yeah. And yeah, so similarly, we get such a result. Yeah. We think about all the distinguished element and the degree from 1 to n, and your minimal irreducible polynomial factor. Yeah. So congruent to F modulo G. Yeah. Okay, so this is the application, all the kind of application. And so next, we also give a connection with the elliptic curve over number field. Okay. Yeah. So you can take an elliptic curve, and your A and B is the integer. So delta E is the discriminant idea. We take some good prime idea, or you can think about something like unnomified, yeah, stuff. So which is not divide this discriminant idea. So now we think about the reduction modulo P. So we get another elliptic curve because this is a good prime idea. Now we define the AP. So this is a trace of flow beneath. So it's 1 plus Q minus, so the number of the solution when you think about the kind of a local weight. Yeah. Okay, so Q is a cardinality of the F of P. Now we think about the function field corresponding to this elliptic curve over the F of P. Now we have the observation. So the degree 1, all the degree 1 guy actually just consists of all the solution. Yeah. Now by this observation, we can rewrite our AP in terms of Mobius function, because this is a prime. So minus the mu of P just minus 1. And we divide by norm of P, which is just Q, and we multiply Q. Why we did this? Because we would like give some connection with our main result. Okay? By our main result, so in this special case, you take the S, it's just the whole set. So you have the natural density just 1. Now you do some simple calculations, so multiply Q and plug inside. So you get such a relation. You might can think about it more because by modularity theorem, so we know every curve, this is corresponding to the modular form, a new form of weight 2. So one can try to maybe generalize this kind of a connection in terms of any weight K, yeah, of a modular form. Okay. So right now we are working on imperfect, so we try to get a generalization. Like we think about the other kind of a function. So this is analogous result of Worm's result, but this is over function field. Yeah. So we have the almost the same assumption, and you think about the Dirichlet convolution. Yeah. And so we are, yeah, so this theory actually already proved, yeah. So, but we are still working on the writing. And so I think that's all I want to talk about. And thank you very much.
Great. Thank you very much. Let's take our speaker. Questions? So I will ask a question. So okay. These kind of formulas, both over number fields and over function fields, where you have sums over primes or products of primes, and you get like something exact, or completely amazing to me. In what generality, roughly, do you expect these kind of formulas to be true?
So actually we are, yeah, so that's a good question. So actually we are trying to generalize to like a abelian semigroup. Yeah. Mm-hmm. So yeah, it's an abelian group. So we are trying to work on it. Yeah. So we still think of, you try to generalize to more general way like that. Yeah. So because this is a function field, if you look at the definition, this is basically just abelian group notation stuff. Yeah. And the number field, this is just a multiplicative version. Yeah.
Great. Other questions? Okay, let's thank our speaker again.
Thank you.
And let me stop the recording.